After talking about magnetism in nanoparticles, let us take up the topic of magnetism in clusters. Early on we had said that we could actually divide into materials into three size regimes. One is what we call small clusters, one we call large clusters, and one we call nanocrystals. And this division of properties was based on a variation of a property and with the what we call addition of removal of more number of atoms. And in fact, magnetism in some sense is an ideal property to make this kind of a distinction between what you might call a small cluster, a large cluster, and a nanocrystal. We said that clusters or small clusters are that size regime wherein the addition or removal of a mere atom can cause a large variation in the property. And here of course, we are talking about a property like a ferromagnetic property of a cluster of atoms. This is important to note because even you are in the nanocrystal size regime, a mere addition of or removal of atom does not cause a serious change in the properties. In other words, there is a small change, but that is not significant with respect to the already existing value of the property. So, these clusters are size regimes which are usually small and less than about 5 nanometers. Typically, we want to consider clusters wherein we can actually count the number of atoms like a 13 atom cluster or a 25 atom cluster or a 50 atom cluster. So, these are the real size regimes of clusters wherein we are really interested, and in the limit what you might call in the large size limit, what we obtain is called the bulk limit, wherein you consider a large nanocrystal. Now, when you are talking about magnetic behavior or ferromagnetic behavior of clusters, a few important points have to be kept in mind. This is of course the atomic structure, and here we may note that this atomic structure need not be crystalline. In other words, this could just be a cluster which has its own structure, and this is not necessarily a crystalline kind of a structure. We have to worry about the nearest neighbor atom distance in the cluster, and of course, there could be more than one nearest neighbor distance depending on the size of the cluster. Or of course, there could be one nearest neighbor, there could be one other distance which is very close to the nearest neighbor distance. Then of course, the purity and the defect structure of the cluster is also very important, because manufacturing some of these clusters is very difficult, and getting a right number of atoms and later on of course, separating those cluster sizes based on mass spectroscopy and studying their properties is indeed an important challenge. When you are talking about ferromagnetic clusters, we identify the regime of small clusters with about less than about 20 atoms. And here there is large oscillations in the magnetic moment of the cluster, and of course, we are talking about the magnetic moment per atom. We already noted before that when you are talking about a property like magnetic moment, when you decrease the size of the or the scale of the system, the magnetic moment increases above the bulk value. Now, we will be noting that how this behavior becomes really drastic when you are talking about small clusters. And when you are talking about a large group of atoms like more than 600 atoms, you typically notice that bulk like behavior emerges. That means, with increasing number of atoms, the oscillations in the property, here of course, the magnetic moment dies down, and therefore, there are no sharp variations with change in number of atoms, and actually the bulk behavior emerges. So, we have 2 or 3 size regimes, that means small clusters having typically less than about 50 or 20 atoms, the big clusters from 50 atoms to say 600 atoms, and finally of course, the bulk behavior wherein you can think of what you might call the magnetic moment approaching that of the bulk value of iron. Now, we already noted that iron can have a maximum possible magnetic moment of about 6 mu b per atom, 3 arising from orbital and 3 from spin. We had also noted that typically in bulk iron, most of the orbital magnetic contribution is quenched because of the strong interaction with the lattice. Now, if you take up individual clusters to highlight how the property changes, and this is schematically shown here in this graph here. You are studying the number of atoms in this cluster. This is no longer a dimension like nanometer, but it is purely a number because we are really in the small cluster regime, and you are studying the magnetic moment per atom on the y axis. Now, so therefore, we can see that clearly there are 3 regimes, what you might call the small cluster regime, which you can see wherein there are the small cluster regime, where you can see that there are sharp variations in the property. Then there is the medium cluster regime, wherein you have oscillations, but they are smaller oscillations, they are oscillations spread over a large number of atoms. That means, over a large collection of atoms, you see these oscillations are taking place, but when you add many number of atoms, not a small 1 or 2 atoms. So, you have this regime which is of interest to us now. you notice that merely by adding one atom and going from this value, you can see that this is the Fe12 cluster and you go to the Fe13 cluster. That means, you are just adding one atom, you notice that the magnetic moment changes drastically. There is a severe precipitous fall in the magnetic moment, and this is what is we call the small cluster regime, a signature of the small cluster regime. And further, when you add one more atom, there is again a sharp increase in the magnetic moment of the cluster, and these oscillations continue in a what you might call in a sharp fashion till you reach about 25 atoms, and after that, of course, we said that the cluster, the variation with cluster size gets a little more smoother, and finally, of course, in the bulk regime you will notice that the variation becomes even more smooth, and you have the bulk behavior emerging. In other words, the ion in the large crystal regime actually approaches a magnetic moment of about 2.2 mu b per atom. In this graph, of course, the lower limit is the bulk limit and the upper limit is what you might call the atomic limit, which is possible, which we said is about 6 mu b, because an ion atom cannot have more than, or an ion cluster cannot have more than 6 mu b, because each atom only contributes about 3 mu b from the orbital motion and 3 from the spin contribution, and therefore, the maximum limit is 6 and all. But nevertheless, it is important to note that all these magnetic moments which you are noting in the graph here are above that of the bulk limit. That means, there is an enhancement in the magnetic moment in the, of course, in the nanocrystalline regime, in the regime of the large cluster, and also in the regime of the small cluster. So, the Fe12 cluster has a magnetic moment of about 5.4 mu b per atom. That means, very little of the orbital motion is quenched in this cluster. So, this is would be like approaching the atomic limit when you have a ion 12 cluster. On the other hand, adding just one more atom, making it Fe13, we notice that it has a much lower magnetic moment of only about 2.44 mu b. Now, if you compare this Fe13 cluster with, for instance, nickel 13 cluster, it also has an abnormally low moment, and this can be attributed to the icosahedral structure of the cluster. In other words, the cluster is densely packed. That means, atomic separation is reduced in this cluster, and we had noted earlier that 3 factors coming into play while designing the magnetic moment of the cluster is the nearest neighbor distance in the cluster, and therefore, if the nearest neighbor distance is coming down, then you have a reduction in, that means, there is an overlap of the atomic orbitals, and therefore, there is a reduction in the magnetic moment. With larger and larger cluster size, the orbital contribution seems to be low, but there is still an enhancement of the magnetic moment over the bulk value. This we had noticed before, because this is purely coming from the reduction in the size. The structure and packing fraction seem to play, or packing method seems to play an important role in the net magnetic moment obtained when you are talking about these clusters of magnetic atoms. So, to summarize this story of the ferromagnetic clusters, we can divide the ferromagnetic clusters into nanocrystalline regime, where the oscillations are small, the small cluster, large cluster regime, where there are oscillations, but this spread over large number of atoms, and the small cluster regime, typically less than about 20 atoms, wherein there are serious variations or sharp variations when you add or remove an atom. And you can see that the ion 12 cluster actually goes very close to the what you might call the theoretical possible limit for an, which is close to the atomic magnetic moment of ion. On the other hand, there can be clusters like the Fe13 cluster, which are close packed clusters having icosahedral configuration, which give you actually a low magnetic moment. After talking about the ferromagnetic material like iron, let us talk about what you might call the anti-ferromagnetic clusters. Now, when you are talking about anti-ferromagnetic clusters, these are actually not anti-ferromagnetic in the cluster zone, they are actually what are anti-ferromagnetic in the bulk. So, for instance, we know that chromium is one of the one of the few elements which are antiferromagnetic, like manganese, and therefore, in the bulk form, chromium or manganese is expected to be antiferromagnetic. But here we are talking about antiferromagnetic materials in the bulk, which have behaving like ferromagnets in the cluster zone. That means, when you are making the small clusters out of these antiferromagnetic materials in bulk, you are actually getting ferromagnetic property. Again, a very interesting observation, that because we have these materials do not behave like ferromagnets in the bulk. In antiferromagnetic materials, we do not expect any net magnetic moment in the bulk, because the upspins and downspins cancel themselves out. However, there is a possibility that a small cluster in a small cluster their up and down spins do not cancel out, leading to a net magnetic moment. Of course, this magnetic moment is not because this is now a small residual non cancellation, and this is not expected to be as high as that you see in a ferromagnetic cluster. But nevertheless, this is an interesting possibility. In these small magnetic clusters, frustration is also an issue, and this frustration leads to the fact that the spin on a given atom does not know which way to point. In other words, if I had a large system, then I know in an antiferromagnetic material, if I had spin arrangements ups and downs, they will go like this. But in a small crystal, there could so happen that there is one spin which is introduced here, there could be an atom here, which does not know that if this spin has to be up or down, and this automatically implies that it is not following the antiferromagnetic order, and therefore, there could be a net residual spin up or spin down coming from the fact that atomic position has been frustrated with respect to the remaining of the lattice. We will take up two examples to understand antiferromagnetic clusters. One is the example of chromium and one is the example of manganese, because these are elemental, but having said that if they are elemental, it does not mean that their overall magnetization states are easy to understand. Now, if you take up the example of manganese and study now like before the number of manganese atoms in the cluster along the x axis and the magnetic moment along the y axis, again you do see what you might call three regimes. One regime which we might call the small cluster regime, one you might call the large cluster regime, and then of course, the nanocrystal regime, and finally, you have the bulk limit. The bulk limit in this case clearly is the case where there is 0 net magnetic moment, because you know this is an antiferromagnetic material and therefore, you do not expect any magnetic moment in the bulk form. So, ultimately this curve has to go down to 0. In the small cluster regime, again you notice that there are sharp variations in the magnetic moment, and you can observe that these sharp variations again can be understood in terms of certain geometry, that for instance, the icosahedral cluster gives you a very small magnetic moment, net residual magnetic moment, while then by adding just couple of atoms you get the n equal to 15 cluster, which is having a very high magnetic moment, but having noted that this very high is only about 1.5 mu b per atom, unlike the case of the very high in the case of the ferromagnetic cluster, where we went up to a value of 5.4 mu b per atom, because these are not inherently ferromagnetic material. These are antiferromagnetic materials which are behaving like ferromagnetic materials in the small scale regime. Therefore, again you see that in these cases there are what you might call minima corresponding to the icosahedral cluster and the n equal to 19 cluster, and we will talk about this in a few moments. But these oscillations tend to die down when you approach the large cluster regime, and then of course, you obtain the bulk limit wherein of course, you ultimately get a 0 magnetic moment. Now, therefore, in manganese clusters show some similarities with ferromagnetic ion clusters with regard to the cluster size dependence, and this is in the regime of more than about 10 atoms. Compact this 13 atom clusters, which is the icosahedral configuration, and the Mn19, which is actually a double icosahedral cluster. So, that means there is one icosahedral shell, and above that there is a second icosahedral shell, which is called a double icosahedral construction, gives very low magnetic moments compared to the neighboring clusters like Mn15, which has a high magnetic moment of about 1.5 mu b per atom. So, the low magnetic moments are about 0.4 mu b per atom, this is in this range 0.4 to 0.5 mu b per atom, while the high one correspond to about 1.5 mu b per atom. So, in the case of manganese, you notice that there is a variation between about 0.4 and about 1.5 mu b per atom based on the cluster size, and again like before in the case of iron, we can understand this in terms of the geometry of the cluster, that if there is a close packed cluster having some kind of a single shell or a double shell icosahedral configuration, then the magnetic moment is small. The case of chromium is slightly more complicated, in fact, it is significantly more complicated, and the reason happens to be that the antiferromagnetism in chromium is supposed to arise from what is known as a spin density wave. So, and often the phrase used is that it is an incommensurate spin density wave antiferromagnet. That means that this is not a simple kind of an antiferromagnet which can be drawn like a picture using this one we saw before. This is the underlying spins have a spin density wave, and this spin density wave, as I pointed out, can actually be incommensurate with respect to the underlying lattice, and therefore, you can have an incommensurate spin density wave, which is actually giving rise to this antiferromagnetism in chromium. And therefore, since this is a very rich system, this also means that there are a lot of complications in understanding such a very rich system like chromium. Though we said that it is an elemental antiferromagnet, this does not make it a simple antiferromagnet, though it is elemental. This is akin to the example of manganese in crystal structures, though manganese is an elemental crystal. Often you know that alpha manganese and beta manganese have actually a very complicated crystal structure having very number of atoms. The plot of magnetic moments oscillates with size, like in the case of the manganese or the case of the ferromagnetic clusters. A cluster size of CR9 is expected to exist in multiple magnetization states, and this multiple magnetization states actually makes the analysis very difficult for us to understand that what is really giving rise to this effect. That means, and in addition to this multiple magnetization states, the issue is of there are many structural isomers also possible. That means that CR9 cluster not only exists in a single structural form, it exists in many other structural isomers, and therefore, these structural isomers, each one of them will have a different magnetization, and the net effect on magnetization you are seeing is actually, when you do an experiment, is actually an average over all these structural isomers and all these multiple magnetization states. The CR9 magnetization can actually be small, it is only about 0.65 μb per atom, or it can be 1.8 μb per atom. That means, a single cluster, I do not mean a single structure structurally, a single number of atoms, 9 atoms in the CR9 cluster can exist, can give you a net magnetization of something like 0.6 μb or 1.8 μb, which means this is a large variation. We already saw that the maxima minima, it is between the almost the maxima and minima in such a plot. Okay. So, such large variations can, it is actually difficult to understand it, and the underlying mechanisms are supposed to be, as I pointed out, the existence of multiple magnetization states and also existence of structural isomers. So, the essential message of studying antiferromagnetic clusters is that there can be materials which are antiferromagnetic with zero magnetization in bulk, but which behave like ferromagnets in the small cluster regime. And in the small cluster regime, like in the case of ferromagnetic clusters, there are large oscillations, and these oscillations finally die down, and you obtain what is called the large cluster regime, and finally the nanocrystal regime. Additionally, we noted that to understand the variation in magnetization in these small clusters, we can invoke the principles we used in the case of the iron clusters. In other words, the icosahedral or close packing in these crystals is expected to give us these large variations in the magnetization. So, so this is a very interesting possibility that actually you are seeing ferromagnetism in small clusters of an antiferromagnetic material. We had seen that the magnetic properties of clusters is a very sensitive function of the number of atoms in the clusters. Before we go on to other interesting magnetic properties of other nanostructures and hybrids, let us consider briefly here the experimental production of clusters and how we can measure the magnetic moment of these clusters. Typically, a gas phase supersaturated in metal vapor is ejected into a flowing inert gas, which is cooled, and at the heart of or the schematic of this kind of a production technique is shown in the figure below, wherein you see that there is a liquid metal bath, there is a gas which is flowing into the chamber. This chamber is at a high suction rate, but under low vacuum. Further, this liquid metal which is in the vapor state is atomized through a nozzle, it passes through a skimmer and goes into a chamber where there is a high vacuum pump, which of course has a low suction rate, but it is a high vacuum pump. So, essentially we have a supersaturated metal vapor which is ejected into a flowing inert gas. The metal vapor itself could be produced by thermal evaporation, laser ablation, sputtering, or many of the other techniques which can produce this metal vapor. Further, we know that now this metal vapor consists of clusters of diverse sizes. That means, they may have right from a few atoms to a few thousand atoms, and we require mass separators which can actually separate out clusters of various sizes. And for this, the clusters typically need to be charged, and if the clusters need to be ionized if they are not charged priorly. So, this is a very important point, because the mass separators will not work, most of the mass separators will not work on non-charged particles. Here we list the name of some of these mass filters, though we will not go into the details of their operation or their physics behind them. These mass filters include radio frequency quadrupole filters, Vane filters, time of flight mass spectrometers, pulse field mass selector, etc. But as we pointed out, all these techniques typically depend on the clusters to be charged, and if they are not charged, as we shall see in a coming slide, that we will charge the clusters before they are sent into a spectrometer, like for instance time of flight mass spectrometer. At the end of the separation, our goal is that we have a narrow distribution of masses of these particles or these clusters, and if you are talking about small clusters, we would even like to get a precise number of atoms in these clusters, because as we have noted before, that in small clusters addition or removal of a single atom can lead to very steep changes in terms of their magnetic properties, like we saw that for the case of the ferromagnetic clusters, where we noted that if you have an icosahedral cluster, it typically has a low magnetic moment, but if you add an atom to it, then the magnetic moment increases steeply. Similarly, so for antiferromagnetic clusters, that we saw that in the small cluster regime, actually we have severe oscillations in terms of the magnetic moment of the particles. Therefore, in small clusters we would like to isolate a precise number of atoms, and as I pointed out, some of these techniques like radio frequency quadrupole filters, Vane filters, etc., help you in separation of these different mass particles, which also imply different number of atoms in these clusters. We should also briefly take up here the measurement of the magnetic moments of clusters. That is, we had already noted that these plots which we have seen are actually experimental plots. That means, people have actually produced clusters of atoms consisting of magnetic material and further have gone on to measure the magnetic moment. So, these are experimental results, and therefore, we need to know how we can actually measure the magnetic moment of these clusters. Though our lecture here would be limited to a brief outline, and students interested in these techniques may consult extensive texts on these aspects further. Now, first we shall talk about experimental results presented for free clusters. Clusters can be of three types. They can be free clusters, they can be clusters which are deposited on a substrate, that means they are on the surface of a substrate, or they can actually be embedded within a material. But here we first take up or we will present in a little detail how can we measure the magnetism or a magnetic moment of a free cluster. For instance, this could be iron ferromagnetic clusters, or it could be chromium and manganese antiferromagnetic clusters, and the typical experimental setup is based on the classic Stern-Gerlach experiment, which was first used to detect the electron spin. Now, typically this Stern-Gerlach kind of an experiment is coupled with a pulse laser vapor deposition techniques, and we shall consider some of these details in the next slide, for instance. So, typically such an experimental setup is what is used for the detection of the magnetic moment. At the heart of such an instrument is what we might call the time of flight mass spectrometer, and the whole setup starts with a cluster source. So, before we take up this setup in detail, let us go ahead with the further points, that typically a collimated cluster beam is guided into a magnetic field gradient. That means, we do not have a constant magnetic field, but a field gradient which is quantified as dB by dZ. The magnetic field gradient will deflect a cluster with a magnetic moment mu by a distance d, and this is given by the equation as here. So, if you have the distance of deflection d under the influence of a magnetic field gradient dB by dZ, then if the particle has a mass m, then this is the equation governing the deflection of the particle. Now, in this equation, L is the length of the magnet, d is the distance from the end of the magnet to the detector, m, as I pointed out, is the cluster mass, and Vx is the entrance velocity, which is assumed constant. Of course, there may be many situations in which the entrance velocity is not constant, and therefore, this would be an simplifying assumption which is used, so that we can approximately find out the distance of deflection. As I pointed out, there are other kinds of magnetic particles, those which are embedded in a second phase in a matrix, or those which are deposited on surfaces. And for clusters deposited on surface, other techniques of measurement exist. That means, the technique mentioned above is not suitable for that purpose, as you will see that in such a technique you need a stream of these magnetic particles, and these magnetic particles will then be deflected by the magnetic field and will be put through a mass spectrometer. For particles or clusters deposited on surfaces, we can use techniques like X-ray magnetic circular dichorism, dichorism in photoelectron spectroscopy, surface magneto-optical Kerr effect, UHV vibrating sample magnetometry, etc. And here we are just mentioning the names. An interested reader obviously needs to go into texts which will go into detail regarding the operation of these techniques and the physics behind them. For embedded clusters, techniques like micro squid measurements, micro Hall probes, etc. can be used for the measurement of the magnetic moments. So, a single technique is not sufficient for us to understand all kind of magnetic clusters, but here we take briefly the one which is used for the measurement of free particle magnetic moments. Just to summarize this slide, at the heart of the experiment is a setup which is based on a technique like the Stern-Gerlach experiment, the classic experiment which measured the electron spin. The physics behind is that you have a magnetic field gradient which deflects the particle based on the mass of the particle and its magnetic moment, and based on the deflection we can then back calculate the magnetic moment on the particle, assuming that the velocity of entrance of these cluster particles is independent of their size and it is a constant quantity. So, this is the brief outline of the experimental setup for the measurement of magnetic moments. First, metal clusters are produced by pulse vapor deposition. Of course, other techniques may also be used for the production of these metal clusters of a target material into a jet of helium gas. Of course, helium we know is inert and therefore, will not react with the metal cluster vapor. The cluster per glass mixture undergoes supersonic expansion on entering vacuum. So, this is the next stage after the production of these metal clusters, that they undergo supersonic expansion when they enter the vacuum. Then the beam produced, so that means here you have the nozzle which produces the beam. The beam produced is collimated and the apertures play an important role in this collimation process. Then further the magnetic field gradient which is produced by these field gradient magnets is used for the deflection of these collimated beam. Okay. But as I pointed out, even though now you have a deflection produced, unless these clusters are ionized, we will not be able to do mass spectroscopy on them. Therefore, these clusters need to be ionized, and the next chamber down the line is the ionization by a laser. So, you have a laser which is specifically used to ionize these clusters, and this laser is different from the laser which is used initially for the production of the vaporized metal. So, this laser has a different purpose. This laser is used for the ionization of the cluster. Finally, after the cluster has been ionized, now their time of flight will depend on the mass and the ionization, and therefore, the mass dependent deflection is measured and is perpendicular to the beam in a time of flight mass spectrometer. That means, initially the beam was arriving in this direction, but now the beam is deflected into the mass spectrometer at right angles to the original direction in which the cluster source was producing them. So, to summarize this experiment, we are now trying to measure the magnetic moments of free magnetic particles, and for that we are using an equation like the one listed here below. We are also using a modified version of the Stern-Gerlach experiment, and the flow chart for this experiment is as follows: that we have a cluster source produced by a laser. This cluster source is collimated, and this cluster source is in mixture with a gas, and therefore, this gas and the cluster source goes through a series of apertures and then a field gradient as shown here. So, it goes through a field gradient, and this field gradient deflects the particles depending on their magnetic moment and their mass. And finally, to detect the particles, we ionize these clusters and finally use a time of flight mass spectrometer to deflect it and finally back calculate the magnetic moment on these clusters. Now, obviously, as we can note that there are issues regarding the measurement of magnetic particle properties of nanomaterials, which are quite unique to nanomaterials and they are quite different from their bulk counterparts. So, needless to say that the measurement of magnetic properties of clusters in nanostructures is challenging as compared to their bulk counterparts. In clusters, magnetic moment is a sensitive function of the number of atoms in the cluster. That means, we need to know the number of atoms precisely. In the case of a bulk, it does not matter to us that if the bulk actually is a 1 centimeter bulk or a 1.1 centimeter bulk, but in the case of nanoparticles and nanoclusters, we need to know that what are the precise number of atoms in the cluster. Coagulation and contamination of these clusters and nanocrystals is a serious issue, and this contamination may take place either during production or during measurements and has to be avoided, because small amounts of contaminants can severely alter the properties of these magnetic nanoparticles. A good example of this would be the surface oxidation of the cobalt magnetic particle. On surface oxidation, you actually form a cobalt oxide on the surface, and the cobalt oxide system has a very different magnetic behavior, which we will consider shortly, and which is at the heart of a phenomenon known as the exchange anisotropy. Therefore, we should avoid any kind of contamination or any kind of reaction with the atmosphere during production or during the measurement process. As you know, temperature plays a very key role in the magnetic behavior of nanoscale systems, because reduction in size is equivalent to increase in temperature, and therefore, when we assume that the temperature of the system is a particular number, we have to assume it is precisely measured and is constant at the level of the cluster and not merely at the average temperature of the chamber. So, not only we should precisely measure the temperature, but control it at the level of the clusters. The spin alignment in nanoscale systems, which we will consider in detail in the coming slides, could be very different from their bulk counterparts, and hence when you try to back calculate using a model or use a model to understand experiments, then the precise geometry of the system and the spins which orientation therein has to be taken into account. That means, we should know the geometry of the nanostructure, we should know the alignment of spins therein in the nanostructure, and we should also take into account the surface effects, else the model will not be able to satisfactorily either understand the experiment or predict properties based on the experiment. In the case of particles in a substrate or embedded magnetic nanoparticles, we have to remember that this is no longer a free system. That means, the properties of a particle which is in intimate contact with, for instance, with a substrate or a matrix is could be very different from the freestanding nanoparticle, and the role of this interface of the substrate could be very pronounced, and often this interface could alter the properties of the nanoparticle altogether. And also, we should remember that if you talk about a single isolated freestanding nanoparticle, its magnetic properties could be somewhat different from that of many clusters placed in proximity. In other words, now the nanoparticles are not free and they talk to each other, and this collective behavior could be very different from that of the single isolated nanoparticle, either free or deposited on a substrate or embedded in a matrix. And therefore, but also we have noted that deducing the properties of freestanding nanoparticles from those measured could be very difficult. In other words, suppose I make measurements on nanoparticles which have been deposited on a substrate, and from there I try to back calculate that what would be the properties of a freestanding nanoparticle. This could be an arduous task and sometimes will not give the correct results. Therefore, to summarize this slide, issues regarding the measurement of magnetic particles are many. A few of them we have taken up in this slide, but as you can see that unless some of the issues regarding for instance, the purity of the nanoparticle, the temperature of the system, the actual knowledge regarding the number of atoms in the system, the kind of models which have been taken into account in the underlying model, like in terms of the spin alignment, etc., have to be specially constructed for these nanoclusters and nanoparticles, and we cannot merely extrapolate from their bulk counterparts. And also we noted last but not the least that isolated nanoparticles could be very different from those which are in proximity to similar kind of nanoparticles or nanoparticles of different types, and therefore, the surrounding medium or the surrounding environment to the nanoparticle or the nanocluster is also of lot of importance when you try to deduce the properties. Next, we take up magnetism in thin films and hybrids, and we had pointed out while we talked about thin films that there are a couple of important things, that in thin films of magnetic materials, ferromagnetic materials, you actually observe what you might call nail walls, which are not found in typically in bulk materials, where you actually observe what you call domain walls, which are called block walls. And interestingly, we will talk about, when we talk about magnetism in hybrids, we will come across very interesting phenomena later on. First, let us talk about this dimensionality of the system. When you talked about previously about the thin films, we noted that the magnetization is in plane and there are no components of magnetization out of plane. Of course, this is only true for very thin films, and when the system size grows, you would note that there is an out of plane component of magnetization or the orientation of the spins, which means the system starts to behave like a 3D system. So, when is this transition from a 2D behavior to a 3D behavior is what we are noting. So, people have studied, of course, these thin films cannot be freestanding thin films, because they would tend to warp and they are difficult to study. Typically, these thin films are grown on a substrate, and in the case of nickel films, which have been studied, on a copper 100 substrate. Of course, its copper is chosen because copper is not a magnetic material. Often you may also notice that in some of these systems studied, the film may actually be epitaxial with respect to the substrate. Now, in the case of the nickel films on copper substrates, and the copper 100 single crystal substrate has been used in the experiment, when the thickness of the nickel film is greater than about 7 monolayers, that means, this is very thin film regime, the systems behaves like a 3D Heisenberg ferromagnet. In other words, it becomes a 3D ferromagnet, that means with spins out of plane, when already the system size is only about 7 monolayers. On the other hand, below 7 monolayers, it behaves like a 2D system. In other words, all the spins are in the plane, while in the 3D system spins can be out of plane. So, this implies that you can have a transition from 2D to 3D behavior in these nickel films, which are grown on copper substrates, for a very thin size of film, like about 7 monolayers. So, below 7 monolayers, you actually have a 2D system, wherein all the spins are in plane, and above 7 monolayers, the system starts to behave like a 3D ferromagnet, wherein the spins have an out of plane component also, which means that now correspondingly the Neal wall, which we talked about, wherein all the spins are rotating in plane, would also have a certain out of plane component in such kind of systems. If of course, we are now, that means that we are talking about a multi domain system in the film, if you have to consider that. The next thing we talk about in these thin films is the case of the Curie temperature in thin films. We had noted earlier itself that the Curie temperature actually varies with size. In the case of iron 100 films grown epitaxially on the silver 111 films, that means, my substrate is now silver 111 substrate, and you are actually growing a iron 100 film on it. And again, we are in the what you might call the very thin regime, wherein we are tracking the layers layer by layer, that means, it is 1 monolayer or 2 monolayer or 3 monolayer. Now, when you are talking about these thin films, we notice that the Curie temperature can actually be reduced with respect to the bulk value, because we already told that decreasing the size in some sense is like increasing the temperature, and when you increase the temperature, what happens is that there is a ferromagnetic to paramagnetic transition, which means that actually you are crossing the Curie temperature. So, this is clear. So, when I plot the thickness of these monolayers with respect to Tc, and of course, now I am normalizing this Tc with respect to the Tc of the bulk material, which is what we normally call the Curie temperature, you would notice that of course, for large sizes of monolayers, more than about 50 monolayers, you approach the bulk limit, that means, Tc by Tc bulk becomes 1, but as you go down to the very thin monolayer regime, the Curie temperature actually falls. In other words, in this very thin monolayers, less than about 20 monolayers, you can see that the exchange coupling is not able to fight against the thermal disordering that effectively, because there are not enough number of atoms in this layer, which implies that the Curie temperature is going to be reduced. In the case we are talking about here, the iron 110 film on silver 111 substrate, the Curie temperature can actually be depressed by about 100 Kelvin with respect to the bulk. That means, you can approach about 10% of the bulk value when you are in the regime of about 1.5 monolayer thick films. That means that in these thin films again, like because it is a reduced dimensionality system, the thermal disordering effects become very important on magnetization. So, therefore, though there is this possibility we introduce that in a reduced dimensionality system, there is this enhanced magnetism per atom we can obtain, that means, the number of Bohr magnetons I get for an atom increases, that possibility is there, but then this is also fighting against thermal disordering effects, and therefore, we will have to cool the system to actually obtain that value of the what do you call the potential magnetization per atom. Before we take up what you might call magnetism in hybrids, let us summarize this slide by saying that in very thin films, you have a 2D kind of a behavior, and this very thin we mean is in the order of a few monolayers. And here, as I pointed out, we are not really studying freestanding thin films, because freestanding thin films are difficult to study. So, these are typically films which are grown either epitaxially or otherwise on some kind of a substrate. Typically, the substrate used of choice is a non-magnetic material like copper or silver, which is a single crystal, and these single crystalline overlayers, when they are in the small size regime, typically behave like 2D system, and later on they start to behave like a 3D system for thicker sizes. Additionally, these very thin films can actually have a depression in what you might call the Curie temperature with respect to the bulk of a large value. That means, it can actually reduce to about 10% or more for very thin films, for when you are trying to find the Curie temperature of these thin films. Next, we take up magnetism of hybrids, and in this context we will take up the important phenomena known as giant magnetoresistance, or called as GMR for short. It is important to know, we had earlier noted a concept known as the anisotropic magnetoresistance, and we had noted that magnetoresistance value is typically about 5%. That means, in the presence of the magnetic field and in the absence of the magnetic field, the resistance value changes only about by 5%. We had also talked about an important concept in that context, that was the concept of the spin dependent scattering. That means, the resistance is coming from a new kind of a phenomena, which is not the usual charge scattering arising due to phonons or impurities, but what we might call the spin dependent scattering. The important thing in giant magnetoresistance, the word giant implies that the change in resistance could be of the order of 80% or more. So, this is a very important point, that is why it is called giant magnetoresistance. And there is also a related phenomena, or a different kind of phenomena known as colossal magnetoresistance, which we will not talk about in this course, but this giant magnetoresistance is not the same as colossal magnetoresistance. Another important point about giant magnetoresistance is that is actually found in hybrids. That means, it is found only in composite structures. There are cases where giant magnetoresistance has been reported in other kind of systems also, but the classical system is that of an hybrid. So, what is the configuration which is giving me this giant magnetoresistance? It is typically a non-magnetic layer lying in between two magnetic layers. This is of course the simplest configuration you can think of. Let me talk about, for instance, in this case example given here, you have two layers of iron, which is ferromagnetic, and there is a non-magnetic layer like chromium. The thickness of this chromium layer is very, very important, as we shall see soon, and typically it is of the order of about 9 angstroms. The thickness of the iron layer is about 30 angstroms. Instead of making one single sandwich structure like this, you could actually repeat this structure to form a larger layer structure consisting of these irons and these chromiums, and this kind of a multi-layer superlattice structure can actually give you an even higher enhanced value of giant magnetoresistance. But the overall physics can easily be understood by considering only a 3-layer system consisting of two ferromagnetic materials and a non-ferromagnetic interlayer between the two. Of course, it is, as I told you, the non-magnetic layer's thickness is very, very important, and it has to be of a very specific size. The reason is that depending on this size of the non-magnetic layer, there is an anti-ferromagnetic coupling between the two layers of iron. That means, the two layers of iron, one layer has magnetization pointing in one direction and the other layer has magnetization pointing in the other direction. I have chosen a configuration known as the magnetization in plane, and there are other configurations where magnetization perpendicular to plane also is possible, but the essential physics again does not change. So, in this case you have one magnetic layer which is pointing in this direction. That means, all the spins in this top layer is pointing to the right, while all the spins, of course, again we are ignoring the interface spins which could be little distorted and the surface spins which could be distorted, we leave that out, and in this layer all are pointing towards the left. This anti-ferromagnetic coupling is a weak coupling coming from a phenomenon known as the RK-KY type of coupling, and in RK-KY coupling, depending on the distance between the two ferromagnetic layers, the coupling can either be ferromagnetic or can be anti-ferromagnetic. That means, if I have my two layers at a certain distance, if it is of course joining together, then it will be ferromagnetic coupling. At a certain distance, it will become anti-ferromagnetic coupling. At a certain larger distance, it will become ferromagnetic again. That means, there is an oscillatory coupling between these two layers, and this is called the RK-KY coupling, coming from authors whose names start as Ruderman and Kittel. Therefore, so you see that this is at the heart of the understanding of the what you might call giant magnetoresistance. In other words, there are two layers, and in the absence of any external magnetic field, the two layers of the ferromagnetic material are anti-ferromagnetically coupled. I am not saying they have become anti-ferromagnetic, these individual layers continue to be ferromagnetic, but the coupling between these two layers, which I call layer 1 and layer 2, are anti-ferromagnetic. That means, they point in opposite directions. Now, what happens when you are passing a current? And when you pass a current through a ferromagnetic material, then the current becomes spin polarized. And when the current, that means, when you are passing a current in a normal material, the spins are pointing randomly, while if you pass the current through a ferromagnetic material, the spins get polarized, because now all the spins in the ferromagnetic material are pointing in the same direction. That means, now you have a spin polarized current. That means, not only is the charge being transported to the ferromagnetic material, spins are also being transported to the ferromagnetic material. Now, let me draw this schematically like this. So, now you have a ferromagnetic material in which all the spins are pointing upwards, say for instance, and now you have a material which is non-magnetic. For now, I will assume that this is again a long piece of material which is non-magnetic. So, when I pass current through this material, this spin gets spin polarized, the current which is flowing. This of course, the fixed charges on lattices, so this fixed magnetic moments in the material, but this is the one which is carrying the current, and that thus I am drawing separately in lead, and therefore, the current, the charges become spin polarized, and this is travelling. Therefore, when it crosses the interface, this material is non-magnetic, and this spin polarization would actually die down from after a certain length, and this length is called the spin diffusion length. In other words, in the magnetic material, when the current is flowing, it becomes spin polarized, but since this material is non-magnetic, there is no internal field or no internal spin polarization to keep the current as spin polarized, and after a certain distance, when it travels in the non-magnetic material, it loses its spin memory. In other words, it becomes, after the spin diffusion length, its spin memory is lost, and it becomes, the spins become randomly oriented. Now, the important point to note is that this intermediate non-magnetic layer has a very small thickness. That means, typically its thickness is less than the spin diffusion length, which implies that the spin current flows across the non-magnetic layer without the spin memory being lost. So, that is a very important point. So, I have a spin polarized current coming from the top layer, which goes down to the bottom layer. Now, what is happening? Initially, since the magnetization of the first material is in this direction, if there are any spins in the current originally pointing in the wrong direction, like for instance, you might have a normal conductor actually injecting electrons into this ferromagnetic layer, those spins will get scattered preferentially, which are pointing in the wrong direction. That means, this kind of a spin which is pointing to the left will get scattered more preferentially, as compared to a spin in another electron which is preferentially oriented with respect to the magnetic field. So, spins which are wrongly pointed get scattered, and now this resistance, that means, if they are scattered, that means, it is contributing to resistance, and this is purely coming from spin polarization related scattering. That means, it is spin related scattering and not the usual phononic or impurity kind of scattering which we have talked about before. So, this is a new kind of phenomena, and therefore, what is happening here is that you have resistance arising from that, and therefore, when the charges cross this interface and come to the chromium layer, you have a spin polarized current in which all the spins are pointing towards the right direction, which is the direction of magnetization in the layer 1. And this spin polarized, as I pointed out, this chromium layer is thin enough such that it is smaller than this spin diffusion length. That means, that when it goes to layer number 2, you have another magnetic layer, but unfortunately, this magnetic layer, the magnetization is in the opposite direction with respect to the first one. That means, there will be a strong spin dependent scattering in the second layer. The layer 2 will scatter all these electrons very strongly. In other words, you will have an high resistance state. So, this is very, very interesting. Now, that I am producing a high resistance state just by antiferromagnetic coupling two layers by using a spacer layer and using spin dependent scattering as a mechanism for increase in resistance. So, you have a high resistance state in the absence of any external magnetic field. Now, suppose what happens when I put an external magnetic field H. What happens now is that in the presence of an external magnetic field, the magnetization vectors in the bottom layer are also pointing in the same directions, and we already noted the spin polarized current in the middle layer when it crosses is pointing towards the right. So, when it comes down to the bottom layer, there is nothing which is impeding it. In fact, it is going to reinforce the spin polarized current and the current can flow unimpeded. That means, you have obtained a low resistance state. In the presence of a magnetic field. Of course, why is this external magnetic field easily able to switch the magnetization direction? Because we said that this RKKY coupling is actually a weak coupling, it is not a very strong coupling. So, when you apply an external magnetic field, this weak antiferromagnetic coupling is overridden and you have both the magnetization, both the layers, layer 1 and layer 2 pointing in the same direction. So, now we have a very interesting effect which is coming from which is definitely in the domain of nanomagnetism, coming from composites or hybrids made of magnetic layers. And of course, you have to, as I pointed out, you have to include a non-magnetic layer which could be a conductor as in this case, or could be a resistant or a dielectric as we shall see in the next slide. So, to summarize this slide, number 1, you could have very high values of magnetoresistance which are called giant magnetoresistance, which is coming in hybrids which exceeds the value of about 80%, unlike the case of normal anisotropic magnetoresistance where you expect a value of about 5%. That means, the state in the presence of the magnetic field is different in resistance from the state in the absence of a magnetic field, and there is this difference is of the order of 80% in these structures. A typical structure consists of two ferromagnetic materials which with a spacer in between with a very small thickness of about 9 angstroms, and this spacer plays an important role of antiferromagnetically coupling the two layers, which they themselves are very thin. This is of the order of 3 nanometers, you can see that the layers, and actually you can make a multi-layer superlattice which will give you an enhanced value of this effect. The essential at the heart of it is two phenomena. One is the weak RKKY coupling leading to this antiferromagnetic coupling. Number 2 is the spin polarized current, which is and spin dependent scattering giving rise to resistance. And finally, noting that in the presence of a magnetic field, I have a low resistance. That means, now I have a control to switch this material from a ferromagnetic or a low resistance state to a high resistance state by using an external magnetic field, and therefore, I have control over the resistance of the material by using an external magnetic field. This gives us a lot of interesting rich possibilities and important applications. Now, some of these applications we will cite in this slide. I had pointed out that when you are dealing with the system, I can actually replace this non-magnetic layer in between with what you might call as a dielectric material. Now, before we come to that, we will talk about another interesting structure which is based on this concept, which is the concept of GMR in sandwich structures. A spin valve GMR also has been devised. In a spin valve, the two ferromagnetic layers have different coercivities and can be switched at different field strengths. So, we are getting additional control here. In earlier we applied one magnetic field and we got the antiferromagnetic or ferromagnetic coupling, but here what we are doing is that we have different coercivities for the two layers and we can actually switch one of those preferentially. So, this is what you may call the spin valve structure. Now, and this spin valve implies that now I am able to control the spin dynamics, which means that I enter a new domain known as the spintronics, wherein I can manipulate charge into electronics. I am able to control the spin of materials and do spintronics. So, this is a very interesting domain which is of magnetism, which is gaining prominence of recent times. And as I pointed out, that an extension of spin valves can be obtained by replacing the non-ferromagnetic layer by a thin insulating layer. A thin insulating layer is otherwise called a tunnel barrier, and in this corresponding case, the effect is known as tunnel magnetoresistance. The critical difference between the two is that in the previous case of giant magnetoresistance, the interlayer was a conductor, that means the electrons could easily flow. In this case, it is an insulator, that means that now the electrons can have to tunnel through this barrier, and we have already discussed about the concept of tunneling. That means that with the thickness of the tunnel region, the resistance increases exponentially. But the important thing is that the overall impedance of the system is large, and therefore, it can be matched to the circuit impedance to obtain a matched system. In TMR, the tunnel magnetoresistance phenomena, spins travelling perpendicular to the layers tunnels through the insulating layer, and hence is the name of the effect. So, this is very similar to the giant magnetoresistance phenomena we saw before. The important difference being is now the current through the insulating layer is a tunneling current, and therefore, is much reduced in value as compared to the GMR case, wherein you had a conducting material like chromium as the interlayer. The TMR effect and the other GMR effect etc., have found important applications, which include hard drives with increased areal densities, magnetoresistive random access memory, which is called the MRAM, and other important applications. These also form a fundamental unit in spin electronics, as I pointed out, with applications such as reprogrammable magnetic logic devices. So, these are important areas of research, wherein lot of intensive research is going on to build better and better higher density storage devices and devices which can be integrated with the current technology, silicon technology. So, therefore, we have seen two important effects, the GMR effect and the TMR effect, wherein magnetoresistance is the heart of designing important devices. Next, we continue with the topic of magnetism in hybrids, and we talk about a phenomenon known as exchange anisotropy. Now, in exchange anisotropy, you again have a composite. In this composite, there is a layer which is antiferromagnetic, and there is a layer which is ferromagnetic. Though we are showing here it as a linear configuration, in reality this could be actually a particle, like what you might call a core shell kind of a structure, which we have dealt with before, and this could be the COO particle, and this could be the CO, and this external layer is the ferromagnetic layer. So, this is the ferromagnetic layer, and the inside layer, the core of this structure, is the antiferromagnetic layer. So, we are actually now focusing on this interface region between the two. So, this is the region we are zooming in on this picture. So, this kind of a configuration is what we are seeing. So, we have an antiferromagnetic layer and a ferromagnetic layer in adjacent to each other. Due to exchange of spins, coupling of spins across the interface between the ferromagnetic phase and the antiferromagnetic phase, there is a preferred direction, that means there is anisotropy for field, which lead to a shift in the hysteresis loop, as we will of course see why this is happening very soon. In other words, in the example you have cited, the cobalt oxide particles are the ferromagnetic particles, and they are covered with an cobalt oxide, which is a antiferromagnetic system with a large crystal anisotropy. So, what we see in this phenomena of exchange anisotropy is that there is a large coercivity increase, and this coercivity increase is coming because now you have made the system highly anisotropic. That means, the ferromagnetic system highly anisotropic by coupling it with an antiferromagnetic layer, which is shown schematically on the right hand side. So, now I obtain high coercivities for this ferromagnetic layer on the left hand side, and this is coming because of the anisotropy introduced by the geometry. Now, this is an externally enforced anisotropy by coupling it with an antiferromagnetic material. The steps involved in creating this exchange anisotropy are as follows. First, of course, you have a single domain ferromagnetic particle like cobalt in this example in contact with an antiferromagnetic material like cobalt oxide. And you would, of course, we have already noted that this antiferromagnetic coupling is actually mediated by a phenomenon known as super exchange by these oxygen molecule, oxygen atoms. So, that means that this coupling between the two antiferromagnetic coupling is mediated by a super exchange, wherein oxygen plays the important role. Now, what we do is that we take the system above the Néel temperature of the antiferromagnetic phase and saturate the ferromagnetic phase. That means, now above the Néel temperature, the antiferromagnetic phase has become an paramagnetic phase, and above that we saturate the ferromagnetic phase. Now, when we cool the system below the Néel temperature of the antiferromagnetic phase, we introduced a preferential alignment of spins across the interface in the antiferromagnetic phase. That means that originally, of course, if I did not have the left hand side of the picture, that means if I had only the right hand side and we did not have the interface, what could happen is that the antiferromagnetic phase could have across the interface spins pointing either upwards or it could have been spins pointing downwards when you cooled below the Néel temperature. So, this could be all spins pointing downwards. So, these two possibilities, this or this, could exist, but now since there is a ferromagnetic phase which has a preferred orientation, you see that the spins are matched across the interface when you cool down below the Néel temperature of the antiferromagnetic phase. Now, the spins in the ferromagnetic phase will maintain their orientation even after the field is removed, because how did you get that preferential alignment towards the top originally in this ferromagnetic phase above the Néel temperature? We used an external magnetic field, right. Now, because now when you remove the external magnetic field, the spins in the ferromagnetic field do not sort of lose their orientation, and that is because there is this antiferromagnetic layer which is imposing the antiferromagnetic across, imposing itself on the ferromagnetic phase on the right. So, that means the ferromagnetic phase now retains its orientation, which is now coupled to the antiferromagnetic layer. Now, we have made the desired composite or the what you might call a structure, and we can now construct the usual MH loop. If the field is removed, the spins in the ferromagnetic phase will flip to the field cooled orientation due to the influence of the antiferromagnetic phase. As the field direction is reversed, the spins across the interface in antiferromagnetic phase with large crystal anisotropy oppose the reversal of spins in the ferromagnetic phase, and this exchange coupling leads to the large coercivity value. So, now having made a structure like this, I can construct what you may call an MH loop, which we normally do, and while this field is pointing in the direction of the ferromagnetic phase, there is no problem, the magnetization is very easy and you can easily obtain the saturation. But when you are trying to put the field in the opposite direction, as in the graph below, the fact that the ferromagnetic layer is now constrained by the antiferromagnetic layer, and the spins in the antiferromagnetic layer cannot switch to the opposite direction of the field or of the spins across the interface, because now this is a material with high exchange anisotropy or high anisotropy. That implies that these spins sitting across the interface will somehow try to what you call tell its neighbors in the ferromagnetic phase not to switch its spins, directing towards the magnetization direction which is externally applied. That means that there is going to be a large coercivity, a large amount of field you need to employ, so that all the spins start to point in the direction of the field, and this implies that you are going to get a high coercivity in an MH loop. In other words, what you are seeing is that, and of course, when in an MH loop we already pointed out, the coercivity is called the intrinsic coercivity. In other words, this is as if the loop originally which was shaded in gray here has shifted to a left, and therefore, you are getting a high value of anisotropy. So, to summarize these slides, to see how we are actually obtaining a new phenomena known as exchange anisotropy. So, we have already noted that anisotropy in materials, in ferromagnetic materials, can come from shape, can come from stress, or the inherent anisotropy which is called the magnetocrystalline anisotropy. Here we are creating an anisotropy by making an hybrid, and in this hybrid there is an antiferromagnetic layer in touch with an ferromagnetic layer. And an example we saw was the cobalt particles in touch with the cobalt oxide particles. In other words, you leave cobalt outside, it gets oxidized and you get this combination. Now, to get the desired high coercivity effect or the exchange anisotropy effect, what we do is that we make a single domain cobalt on an antiferromagnetic cobalt oxide layer. We heat the system above the Néel temperature and apply an external magnetic field to saturate the ferromagnetic phase. Then we cool the system below the Néel temperature, and that implies that the antiferromagnetic order is now dictated by the ferromagnetic phase and the spins across the interface pointing in the same directions. Out of the two options we said, one of the options is chosen as the spin up option, because the spins are up in the ferromagnetic phase. Then of course, what we do is that we can go ahead and construct what we know as the usual MH loop. While constructing the MH loop, in the forward upward direction of the spins, there is no problem, magnetic field pointing upward. When the magnetic field points downward, the ferromagnetic layer wants to switch to the down spins, but because there is an coupling across the interface and the cobalt oxide has high anisotropy, this implies that the spins in the ferromagnetic layer do not want to change their orientation across the interface. They are coupled to the spins across the interface, and therefore, this is as if those spins are holding them in an upward direction, That means that I have to apply even larger field to actually cause this reversal of spins in the ferromagnetic layer, which implies that my coercivity value is going to be high. So, this is the case of the what you might call the exchange anisotropy. So, therefore, we have seen two important effects arising in hybrids, one is the giant magnetoresistance and the other effect of the exchange anisotropy. Now, let us take up some nanostructures or materials with actually a certain specific dimension, and let us see the spin states of some of these. It is important to consider at least a few examples here, because the spin states of these nano dimensioned objects can be very different from the bulk counterparts. We already seen how the spins are oriented in a bulk, that they are divided into domains, and within domains spins are oriented parallel. And of course, only in the domain wall that you obtain a slightly more what you mean complicated configuration of spins, which means that spins would actually start to rotate. So, we talk about, first we take up the example of nano discs, wherein there are special spin arrangements with no bulk counterparts. In 15 nanometer thick permalloy discs with the diameter of the disc greater than about 100 nanometers. So, these are thin discs having a large diameter. So, these are like thin discs like these. If you look from the side, they are thin discs like these, and the thickness of these discs is of the order of about 15 nanometers, and the diameter of these discs is about greater than about 100 nanometers. So, they are thin discs. The spin arrangement in these kind of nano discs consists of concentric arrangement of spins on the outside and with out of plane component toward the center of the discs. Of course, this is schematically shown here like this. In the case of the spins on the outer side of the disc, they are concentric, but in the center they are pointing upward. This z displacement does not mean the spins have come out of the disc, it just implies that the magnitude of the magnetization is large. That is what we are implying by pointing the z displacement. The core radius, wherein the spins are out of plane, is of the order of the exchange length, and exchange length is defined is a characteristic length of a magnetic material below which exchange forces are dominant over magnetostatic effects. We know that when magnetostatic effects are dominant, then spins in a domain will be aligned, and when neighboring domains could be misaligned. When exchange below the exchange length, it is the exchange coupling between the spins which is dominant, which means that spins will tend to align parallel to each other. So, you can see that in the central region of the disc, which is below the order of the exchange length, then you see that the spins are all parallelly aligned and the magnetization is very large. On the outside, you see that the spins are concentric. So, there is no what you might call analog of this in bulk material. So, this is a very special kind of spin arrangement, and we also see that clearly in this example, that on the outside these concentric spins are like a 2D system. In the center, it is like a transition, it is like a 3D system. That means there is a transition between a 2D to a 3D ferromagnet right in a single disc. So, this is a very interesting kind of an arrangement and we are talking about a large disc because the exchange length is of the order of 5 nanometers. Therefore, we need a disc which is large enough in diameter to actually see these transitions. So, this is a very interesting kind of an arrangement in nano discs. Similarly, when you take up a disc which does not have a core, obviously you would expect or you would have guessed that there is going to be no out of plane component in this, because the core has been removed. And in these nano rings, and these kind of structures are called nano rings, there are more than one possible way of spin arranging itself. This left structure is called the vortex structure, where you see that the spins are going concentric in plane. Then there is something known as an onion structure, wherein spins on one half of the disc is pointing one direction and spins in the other half. So, you see other half are pointing in the other direction. So, that these kind of arrangements are possible. So, one small correction is required here. So, this spin has to point in this direction, and of course, this misorientation of spins need not be across the entire half ring, but it could be only in a small region defined by a sector like this. So, you see that, and this state is called the twisted state of this nano ring. Therefore, you see that more and more interesting and complicated arrangements of spins are possible in these nanostructures like the nano rings and nano discs. And it is interesting to note that suppose I were constructing actually a MH loop or a hysteresis loop in a starting with a vortex structure, then I would observe that I would obtain these other states like the onion and twisted structures during some part of the magnetization hysteresis loop. That means, this state would change from the one from an vortex to an onion or to a twisted state during the magnetization process itself. So, we have taken up two interesting examples of nano discs wherein there are special arrangement of spins which have no what you might call bulk analogues, and you can see that these are the concentric spin states, and in the case of the nanodisk we saw that there is a small region in the core of the disk wherein actually there is spins going out of plane. In other words, the system behaves like a 3D system, unlike a 2D system which you expect a thin disk to behave like. So, with this we come to the topic end of the magnetization in nanostructures and nanomaterials, and we have already seen that magnetization is a very rich field wherein you have very interesting effects, like we have seen the effects of super paramagnetism, giant magnetoresistance, etc. And it is important to note that many of these actually have what you might call very interesting applications and very important technological applications. Next we take up the topic of optical properties of nanomaterials. We had noted that earlier that optical properties essentially come from the electromagnetic structure, and we had noted some of the important concepts like band structure which play an important role in the optical properties. We will see further aspects of optical properties of normal materials and then further proceed to optical properties of nanomaterials in this topic or in this chapter. People who are interested in advanced readings regarding the optical properties of nanomaterials may consult the book by Zhang, wherein he talks in details about not only about optical properties, but also spectroscopy of nanomaterials. First we start, as I pointed out, with a broad overview of what we mean by optical properties, what are the possibilities, then we take up specific examples in nanostructured materials. Many of the optical properties are closely related to the electrical and electronic properties of a material. So, this is optical property is a natural consequence of the electrical and electronic structure of a material. So, this is as expected, but then other factors also come into play, and when we are dealing with optical properties, which includes for instance the arrangement of atoms and other what you might call the spatial distribution of the scatterers, etc., and this plays an important role in determining the optical properties. When one is talking about optical properties, one is usually referring to the interaction of electromagnetic radiation with matter, and though the word optical would imply that we are talking about visible radiation, that means which is visible to the human eye, but in general we have to talk about electromagnetic radiation covering the entire spectrum starting from gamma rays to radio waves and all these interactions with matter can be thought of as optical properties, though often we are restricting ourselves to only the visible part of the electromagnetic spectrum. The simple picture one can start with is by considering a ray of an electromagnetic wave, and you know that the ray is actually a geometrical construct and has no physical reality, and we consider a single frequency entering a medium from vacuum. So, this is a starting picture of what you might think as an interaction of electromagnetic radiation with wave. Now, this ray implies that all the wave fronts in the wave are actually perpendicular to this ray. This ray could be reflected, this ray could be transmitted into the medium and refracted, and when I am talking about a medium, this is my medium which I am shading in yellow, and I imply that this medium has a higher optical density or a higher refractive index with respect to the medium surrounding it, which we consider for now to be vacuum. So, this ray could be reflected, it could be refracted, and it could also be absorbed. In other words, this ray entering the medium could lose all its energy within the medium, and therefore, this does not propagate beyond the what you call, even this is a finite medium, then it does not propagate beyond it, and therefore, you will notice that the wave dies down. Ultimately, of course, all the energy in the electromagnetic radiation will have to be converted into heat, and therefore, this absorption essentially implies that the energy in the electromagnetic radiation is converted into heat. When you are talking about reflection, it essentially means that of course, there is no system which is 100% reflecting or 100% refracting or 100% absorbing. So, you typically have a combination of all these three effects, and one of these may be dominant, like you take a highly polished silver mirror surface, then you would expect that such a system is strongly reflecting, and most of the energy is actually sent back into the medium from which the original ray originated. And here we have seen in the case of refraction that we have drawn a certain configuration which we consider to be what we call a material having a positive refractive index, and we will have a few more things to say that how we can construct structures with negative refractive index as well later. Now, this reflection itself could be specular or diffuse. So, if you take a case of a polished mirror, then you see that the reflection would, you follow something like a Snell's law and you have a reflection, but a rough surface like any wooden surface would have typically a diffuse kind of a scattering, which means that you cannot see images in a case where there is diffuse kind of a reflection and not specular reflection. But suppose I consider from this whole process of interaction of the electromagnetic radiation with matter from a more fundamental perspective, there are only two possibilities of interaction of a medium with electromagnetic radiation. One is scattering, another is absorption, and transmission can be thought of as a forward scattering phenomena. So, you send electromagnetic radiation into wave or a ray into wave, and there could be scattering or there could be absorption. So, these are from a more fundamental perspective. And if you are talking of not about a single frequency entering a material, but there is a wider spectrum of frequencies, in other words you have what you might call a panchromatic radiation, then some part of this electromagnetic spectrum could be absorbed, while other frequencies could be scattered. In other words, you could have a medium which absorbs some frequencies, which transmits other frequencies, and which could actually reflect certain other frequencies. So, this is a possibility when you have a radiation consisting of a large variation in the frequencies. Now, when you are talking about absorption, it essentially means that certain resonance in the material has been excited, which means that the material now can be taken to an excited state by this electromagnetic radiation, and that means that it needs to have a certain bare minimum frequency, because frequency is the handle on energy. We know that E equal to h nu for a radiation, and this frequency is able to excite some kind of a resonance in the material, and therefore, this absorption is taking place. What is the kind of excitation which this material can undergo? These processes include the electronic excitation, the vibrational excitation, or it could be the rotational excitations. A nice example of, for instance, the rotational excitation would be the case of microwave heating in our oven, wherein we note that suppose I send microwave radiation into the microwave oven, then the water molecules which have a natural polar character, that means water molecules are polar, and therefore, they have a net polarization in some direction. So, now what happens is that suppose now I send an alternating electromagnetic wave which consists of alternating electric and magnetic fields, then this water molecule will tend to rotate, its electric field will tend to follow the electric field of the incoming radiation. If the frequency is too high, then it will not couple with it. If the frequency is too low, then the heating is going to be too small. But if at the right frequency, which is of the order of about 3 centimeters or so, the wavelength of the electromagnetic radiation, the 3 centimeter wavelength, then what happens is that the water molecules are able to follow the externally applied field, and which is coming from, of course, from the radiation itself. And since the water molecules are rubbing against each other, this whole process is going to be dissipative, and therefore, overall the water in the food or the water in the tumbler actually gets to heat up. So, these rotational excitations can be possible, and this is a nice example of a rotational excitations. If you are talking about, for instance, phenomena typically like an electronic excitation, which can also take place if there is a critical amount of frequency available, then this absorbed energy could actually be re-emitted when the system relaxes to the ground state again. And finally, of course, we have to note that any energy, we have noted before that any absorbed energy is finally dissipated as heat, and this is called dissipative absorption. Now, the important thing to note between these three kinds of mechanism, the electronic, vibrational or rotational excitations, is the fact that the electronic energy levels are highly separated. So, we can see that the E1 and E0 are separated, and this corresponds to a wave number of about 10,000 per centimeter. So, you need a lot of energy to actually excite, and you can find an equivalence between the wave number and the EVs. So, there is a larger wave number associated with the electronic excitations. That means, you need a lot of energy to excite an electron from the lower energy level in an atom or a molecule to a high energy level. And of course, this could also be a solid you could be describing. On the other hand, you would notice that the vibrational levels, which is the next level, is actually closely spaced, and that means that I require a lower amount of energy, and corresponding wave number is of the order of about 1000 per centimeter, that and if I multiply this 1000 of course by this 1.97 10 power minus 5, I can obtain the value in electron volts, but I require a lower amount of energy to excite the vibrational level. That means that if I am having an electromagnetic spectrum, the electronic transitions are typically excited by the high energy radiations, while the vibrational transitions are excited by a slightly lower energy radiation. Finally, the rotational excitations have an even smaller spacing, which is shown here, or for clarity I will show it here, and that means that I have to impose a very small energy to excite a rotational excitation. So, even though there are 3 possible mechanisms by which I can excite a material, which of course, again this excitation might relax to the ground state again by re-emission of radiation, but these energies are all not the same, and therefore, depending on the frequency of the electromagnetic radiation, one of these might be excited, and therefore, the absorption would be in a certain frequency regime based on the what you may call the energy which is required to excite this. So, and again to go into the detail little more about these excitation, the electronic transitions themselves could be from atomic orbitals, could be from molecular orbitals, or could be to a band, that means an electronic energy level lying in a band. And we have already noted whenever there is a relaxation of a level from a band, then the range of frequency is usually broad, because band is a semi continuous set of energy levels.